Bluink Smart Card is an implementation of smart card functionality within a smartphone app. The app works with out-of-the-box software on Windows and Mac OS platforms. Two standards, GIDS and PIV, are supported by Bluink Smart Card. GIDS stands for Generic Identity Device Specification, and PIV is the US government standard for personal identity verification. This video will show how Bluink Smart Card works and how you can use it for strong authentication into systems and for secure email signing and encryption. A Bluetooth USB smart card reader from Bluink is required to connect the smartphone to a computer and allows the Bluink Smart Card app to appear as a real smart card to the system. Our smartphone on the left has been previously paired with this mini USB smart card reader. Using the Bluink Smart Card app, we connect to the device and insert our smart card. The system now sees the card inserted. Before we can use Bluink Smart Card, we must first create a card. We'll start by creating a GIDS card because we can issue credentials to this card using standard Microsoft software. Using the Smart Card Manager view of the app, we create a new blank smart card, give the card a name, and select which standard to use, PIV or GIDS. Here we've chosen GIDS. Now that we have a smart card, I'm going to issue a certificate to the card that will allow me to use it for smart card logins. This will be done using Microsoft Certificate Manager. In this case, I'm going to issue a certificate on behalf of another user. I first need to select a signing certificate that I use as an administrator to make certificate requests. Next, I select the certificate template. I'm going to pick the one that has the smart card login policy enabled. Next, I select the user from Active Directory that I want to issue the certificate to. The enrollment process is now waiting for the user's smart card to be inserted. On the left, you can see the user's Bluink Smart Card app with his selected GIDS card. I've enabled debug mode so you can see the smart card activity that will occur during this operation. The system is querying the card to discover what kind of card it's dealing with. Once it's ready, I can continue. The user must type in his smart card PIN to allow the security operations to proceed. The smart card generates a key pair and exports the public key. The enrollment server is then contacted to generate a certificate with this public key. Finally, the new certificate is installed on the smart card. The private key in this case has been generated within the smartphone keychain and will never leave the smartphone. The next demonstration will show the same operation to issue a certificate for email security. This time, however, we're going to generate the keys off of the smart card and archive them in the Certificate Manager. I'm selecting a certificate template that is designed for email signing and encryption, and which also allows keys to be exported. We do this to have a backup of the encryption private key, so that if the smartphone is ever lost, any data that was encrypted with the smartphone keys can be recovered. We will also install this same certificate on the iPhone platform as a profile. This will allow the Apple iPhone Mail app to decrypt the same emails that the Bluink Smart Card can decrypt with desktop email clients. To prepare the certificate and private key for delivery to the end user, I will export it to a PKCS12 file and protect it with a password. Once created, the P12 file can be emailed to the user, and the password can be communicated to him separately. Now we'll show how the PKCS12 file can be securely imported to Bluink Smart Card. From an email attachment on the smartphone, the PKCS12 file can be opened directly in the Bluink Smart Card app. The user must enter the correct password that was used to protect the file. The private key and certificate are extracted and installed into the GIDS Smart Card. The card now contains two certificates, one for login and one for email security. Now we'll import the same file to iOS as a profile so that it can be used in the Apple iPhone Mail app. The smartphone PIN is used to allow the install of the profile, and the password for the PKCS12 file must also be used to unlock the file. This next sequence will show how Bluink Smart Card can be used to log into Windows using the login certificate that we previously issued. We select the Smart Card sign-in option from the login screen. Then we connect the Smart Card using the Bluink Smart Card app. The user enters his Smart Card PIN. The Smart Card verifies the PIN and proceeds to perform a digital signature as requested by the login process. The workstation we've logged into has also been configured to automatically lock on Smart Card removal. Bluink Smart Card can use local smartphone authentication instead of having to remember a Smart Card PIN. To enable this, we select the Phone Auth as PIN option in the Settings view. Now when we perform our login on Windows, we don't have to enter the PIN. Simply press Enter and the Bluink Smart Card will prompt the user to authenticate. In this case, the user has Touch ID enabled and can use finger authentication. This next demonstration will show how the Bluink Smart Card will automatically be removed if the user walks out of Bluetooth range of their Smart Card reader. The signal strength meter at the top of the app is showing the connection strength decreasing. When it reaches a minimum threshold or disconnects, the Smart Card will be removed from the system and the workstation will lock automatically. Up until now, we've been using a GIDS Smart Card. However, macOS only supports the PIV standard out of the box. To enable full interoperability of the Smart Card, we can create a compatible PIV card from the existing GIDS Smart Card. We do this using the toPIV function of the Smart Card Manager view in the app. After doing this, the same keys and certificates that were issued to the GIDS card can now be used with the PIV Smart Card middleware. Now that we have a PIV compliant card edge, we can use our certificate to log into macOS. This next demonstration will show how Bluink Smart Card can be used to digitally sign and encrypt emails. On the left, we have a smart card that has been issued to Steve. Steve is writing an urgent and important email to Larry using Microsoft Outlook 2016. Because of the importance of this message, Steve will digitally sign the email using the private key that is carried in his Bluink Smart Card. This will prove to the recipients that the email came from Steve and no one else. Due to the sensitive nature of this message, Steve will also encrypt the email for Larry so that no one except Larry can read it. We'll turn debug mode on once again so you can see the smart card interacting with the desktop email client. Now when Steve hits send, his private key will be utilized to digitally sign the message. The email is also encrypted using Larry's public key. Now we'll show how the email that Steve composed can be read by Larry. Larry is using Apple Mail on macOS. You can see that the email has arrived, but it cannot be viewed. Instead, it shows up as an SMIME attachment. This is because Larry's smart card needs to be used to decrypt the message. To show this, we'll insert Larry's smart card and reopen the Mail application. This time, Larry's being asked to enter a PIN so that his private key can be used to decrypt the message. After entering the PIN, the private key operation occurs and the message is decrypted. We can also see that the email was digitally signed by Steve. In this demonstration, we'll show how the iPhone Apple Mail app can decrypt the same message sent by Steve. We can do this because we imported the email encryption certificate and keys as an iOS profile. Opening up the email in Apple Mail now shows the decrypted message. That's all for the Bluink Smart Card demo. Like, comment, or subscribe on YouTube if you found this video interesting. Feel free to contact us if you want to learn more. Thanks for watching.